Howdy, y'all, and welcome back to another high-powered episode of the High Voltage Live Show, coming to you live here from Denver, Colorado. I'm your host, Willie Snyder with Nat King Code. I am joined by my excellent partner over there at the Volt Online Academy, James Steve Man Stallcup. I'm going to start calling you King James, man. I think that's sticking, man.
Y'all started that crap. Everybody's calling me that now.
But it's really awesome to have you all here tonight, and we have a great show in store for you. We put together some of the greatest myths. I really appreciate having so many people participate. We had some great comments, and most of my pictures are from service calls that I do. And I just run into problems, and then I take a picture of it. I'm like, that's a code violation anyway, you know, but it's fun to do this. And a lot of times I do take pictures of my own work, but I really think that by getting those pictures out there, it kind of helps us all be better electricians. And that's the whole reason I started the Nat King Code page, was to try to help us out in the industry, be like better electricians, and just kind of, you know, show you some examples of stuff. And, you know, people will say, oh, that's a code violation. You're like, well, you know, let's talk about it and stuff. So it's really awesome to have all the participation that I had this week on Myth of the Week. And I always get people coming up to me at the job site like, hey, man, what's up the Will? You know, what's the Myth of the Week this week and stuff. So it's pretty awesome. And this one was kind of a little bit borderline as far as the picture that I used this week was actually a code violation. So, and I really appreciate you bringing all the code stuff too, James. Man, dude, we're putting it on them, man. Them boys are scrambling, man. They're trying to keep up with us, man. It's not easy.
I'm just shocked. Everybody that's on whichever groups we have, you know, there's quite a few of them, but particularly NEC for Dummies. I mean, I just put a post up. Oh yeah, man, we just hit 15,000. I mean, we're almost over 15.5, and that was like first of the week. I mean, it is just exploding, and I think a lot of the reason it is exploding like it is people appreciate the type of content we're providing to it, and I think the High Voltage Live podcast being a part of that, you know, is also helping expanding the reach. And
well, and we're trying to promote everyone out there. You know, if you guys have electrical businesses, go over, type in the Rebs group. They have like a lot of tips to help your business grow, and tips for electrical businesses. And then you have the Fix It Queen on there, and the Fix It Queen has like so much cool stuff on there. So that's something for you guys to check out and help you get better. The NEC Live has been really awesome. Oh, we got David Engelhardt in the house.
Hey, David.
Welcome, David.
Yeah, you know, when we got started with this, you know, I remember us talking. We were like, man, it'd be just great if we could get 5,000 people on, you know, Dummies before the end of the year. And here we're now setting by end of summer, you know, we're going to be close to 20,000 people within 7-8 months time. And like I tell people, you know, I've never said this before, but if you know anybody in the electrical industry, if you just tell one person, 2-3 persons, whatever, we can make this the most dominating electrical code discussion group out there, because it's going to get there eventually. But the members, it depends on you how much you want to see the Facebook group grow. And a lot of that's just telling one person, they tell a person next, and that's how it's grown so fast. It's people telling other people about the type of content that we provide on our groups.
Well, and I've always like asked the members, like, what myth do you want me to cover and stuff. So it's pretty awesome to have like group choice week. And I've had tool of the week choice and stuff like that on the tool page. So just trying to bring it all together. I'm going to go ahead and answer your question, David. When we do our myth of the week, we're going to go ahead and run myth of the week here in a minute.
Oh, yeah. Yeah, we're about to start it. And we're just doing a couple of shout outs to get everything started. I will tell everybody the stuff. I'm right now at the end of chapter 6 of the code change, writing it. So here, I don't know if I'll finish by this weekend, but sometime next week, that book will be written, and I can tell you the illustrations for it. They're halfway through chapter 5 already, and
Nice.
they're moving right along. And I will tell you the illustrations look fantastic. I mean, they're putting extra into it this time. It really looks awesome.
Well, and just to let all the listeners know, we are going to make sure that we post links to that book so you could be the first one to get a stall cup change book this year, which
Yeah,
I'm really excited for. I'm going to have mine. I'll have mine first before anybody. So
yeah, we'll have
just letting
that
you know.
ready right at the 1st of September. We'll probably be the first one out, like we always are. And
Nice.
you'll be able to get that over at Builder's Bookstore. I'll provide links to all of that, and then you give me about take me about November when most of them come out October, November with their code change book. I literally will have the online course coming out by then. So
Sweet.
I will definitely be the first on that with all the interactivity and everything that goes with it. So
awesome, brother.
All right,
Awesome.
let's cue up the myth of the week. What do you say?
Roll it.
Here we go.
It's time for Myth of the Week.
All right. Well, we have an awesome one for you this week. This is one. This stems from a comment that we always hear in the comments all the time in a bunch of groups called "Raceway and a Raceway." So for some reason, I don't know why, this must have started from some code teacher or something back in the day. Is all I can figure. And then they said you can't do this because it's Raceway and a Raceway. Now, this particular install right here is what I call the dick move. These are 3 spare conduits. I showed up to a specific location to add a oven circuit, and I was like, oh, cool, they got spare conduits. And then I see they were all used up by some hognator, when all he could have done was just put a 3/4 connector on there and land all 3 of those MCs into one of those conduits. And it would have made my day a lot easier. You know, I ended up not even messing with that. I just ran a new pipe out of the panel because it was way easier. I didn't want to deal with that, and I just left that. That is actually a code violation. And now they could have actually supported those within 12 inches of where it enters that sleeve, and that could be a compliant installation. But you know, it was just kind of one of those things. So when you go into, as David Englehart mentions, I'm going to pull that comment up real quick. You know, perhaps a cable assembly within a raceway, as long as 312.5 and applicable cable article is adhered to. So that's correct, David. You're absolutely right. And that's where I kind of went with this. And there's really nothing that says you have to strip the jacket off to slide it inside a sleeve, EMT sleeve, any kind of raceway sleeve.
Yeah, and what I did, I went ahead, I threw a few sections here, and I want to show everybody a little bit here. Now, if you look at exception 1 here, where they talk about short sections of raceway, they tell you can use those to provide support or protection of the cable assemblies from what? Physical damage.
Yeah.
Okay. And this is a good section to just start at. That's giving you this type of permission. Now, I also want to show something else here. If you come in and look at 314.17B3, now I'm going to show you 2 things here. Okay. I'm going to show, and I noticed this a while ago at the top. In the next one, I don't show you the 2023 NEC text, but it is 2023. It says 2020, but it's actually 2020.
Okay. I was going to ask you because it looks pretty new.
This here is 2020, but when I come over here and I go to the next one over here, See, that's 2023 because you can see the yellow highlighted.
Okay, gotcha.
Okay? So I also want to point something out here. Now,
Okay, cool.
if you look at this talks about conductors entering through raceways. And it just basically tells you where the raceway is complete between the boxes, conduit bodies, or both, and encloses the individual conductors. And the other one I want to point out here is non-metallic cable assemblies. And then it says, or both, then it says the conductors or cable assemblies shall not be required to be additionally secured. The reason I want to point that out, because I've heard people before say that you can't take and run non-metallic sheet cable in raceways.
Right.
Yes, you can. And somebody brought up, he said, well, there's heat dissipation. Well, you got to remember, when they're doing that, most of the time, when they're running that non-metallic sheet cable in there, it's not being fully loaded. And
or it's less than 10% of the run, which I believe I couldn't tell you the exact reference. I believe it's like 310 and 310 somewhere. It says that if the run is less than 10%, then it's not required to be ambient temperature adjusted.
Yeah, and what they did, one of the proposed changes that we'll get to later down the line, when you come over here, you're going to notice in the heading, they put "and cables." They wanted to be very specific about it being non-metallic sheet cables. And this is just covering that. And then you'll notice it's going to refer you where it's covered in where 300.15C about not being required to be additionally secured within the box or conduit body.
Right. And this one was really funny on the myth, because right when I posted it, everyone, I started getting all these comments like, that's raceway to raceway. I was like, oh man, here we go.
Well, and then if you look, and this does the final tie-in for that, because if you look at 334.15B, it talks about protection from physical damage. So when I'm looking at Article 300, that's general rules there. This is going to be the wiring methods itself, and it says it can be protected from physical damage where necessary by using what? I can use RMC, intermediate, EMT, Schedule 80. It just goes through there, and it tells you it can be used to provide this type of protection.
Right.
So, I saw some of that in some of the comments, and I was like, I need to show people where the code tells you can actually do that, because there is people out there that believe that non-metallic sheet cable can at any time cannot be installed in a raceway. That's not true, because you can be having short sections or something where you're protecting that cable assembly from what? Physical damage.
Yeah, and that's kind of the whole plan that I tried to do with the Nat King code, tying it into the podcast, is that I put the myth of the week out there. And if people say, you know what, I don't agree with you, cool, that's fine. We're totally fine. I mean, if we're wrong, cool, call us out. I mean, we're more than likely to do it to all the rest of the code guys out there. So, we're fine with anyone doing it to us. It's cool.
Well, yeah, and what I tell people, don't take my word for it. I'm just showing you what it says in the text. If you disagree with that, then let me know.
Yeah.
Because I just go by what the code says, and I interpret based on that text. And the text is telling me it's perfectly fine.
Right.
So now I will tell everybody next week, what I'm going to do is I'm going to talk about our working clearance part of the arc flash boundary. Now, the reason I'm going to do that, because there's been somebody out there that has been basically telling some wrong information. And he actually had a video, and I had somebody, I've actually had 3 different messages on this where they've asked me, is the working clearance the arc flash boundary? I said, no. I said, where'd you hear that? And then they tell me, and I'm like, no. And so then I go and show them and lay it out where everything is and show them the difference. And they're like, okay, well, I thought that's how you did it. And I said, well, that's how you do it. And so they took all the sections and everything.
we run into this a lot in multifamily, and like a lot of times they try to place the disconnects to where they have working clearance, and it's almost impossible. I have some really good pictures that I think I'll throw up there, and there's some of them that I think could be interpreted as a working clearance violation, just for the fact that the unit has fuses. But it's hard to say, because if you could check those fuses without it being energized, then it wouldn't be a working clearance violation.
Yeah,
So,
and we'll look at that. I'll go through and explain the language, and I will actually show a direct correlation and tie-in with the 70E document. And also, if I wanted to, I might go ahead and do it. I might even show the direct correlation with 70B as it performs to maintenance also.
well,
And
and typically what these guys do is they'll leave the disconnect energized, and they won't even go open the disconnect or anything. They'll just open the unit and be energized to that unit. So that's not really the electrical worker that's in the danger zone. It's usually the HVAC equipment guy or whoever's like servicing the equipment. So
sure,
that's going to come in with that 70B. So we might be able to tie a little bit of that in too.
yeah,
I'll look into that.
one of the good things that we do, I mean, I forget when we did it, but we did one, and I was showing one of our illustrations, and we had a standard loop in there, and we showed going through the National Electrical Code and then tying in 70E, OSHA, and all that. And the reason that we do that is, like, if you're taking one of the online courses, all of that text will be there. So when you hover above it and you're checking the NEC section, seeing what it says, and then the 70E, 70B, OSHA, whatever we put in there, you can see the direct correlation of what those standards are saying and tying that together. And all of them agree in the same concept. The only time you're worrying about working space clearance is if you're working on it while it's what? Energized. That's it. And we're going to cover that more in depth next week, and I'm gonna have a great. It'll be more like a topic of the week in a way, because there's going to be quite a few illustrations I'm gonna go through, showing the tables and everything and explaining this.
Well, and I won't disappoint anybody. I'll make sure I got some good pictures from the field. This has come up before, where we have VAB units that are in the ceiling, and it's almost impossible for these VAB units to have a 3-foot working clearance. And so, I mean, I've seen multiple times where there's no way you're getting 3 foot up there. And then on top of that, you got 3 foot to say a concrete wall. So that's like a grounded, surface, which is, violation. Got David Englehart in here. What's he got in here?
Yeah, he's dealing with the exception on the 10% or 10-foot rule. Matter of fact, we have an illustration we have an illustration that specifically ties that in, where we show you're coming from the panel board going up, and then you turn up to an AC unit, and we show where you have 10 foot or less and show you how to calculate those conductors and everything.
Nice. I like that, David. So, yeah, that's exactly what I was talking about. It's just something to think about. A lot of these guys think, oh, there's all these rules, and the code is a permissive document, so it's really awesome, especially get guys like David Englehart in here.
Yeah, and we get quite a few different people that come in, and that's one of the reasons I like having the podcast and everything, because we can actually go in and we can discuss all these different variances that are in the code, and how you actually loop through the code in order to get a correct answer, because sometimes it's just not one section. You need 4 or 5 to go through to see what the correct final version of what you could actually do with that installation.
Well, and I guess the most frustrating thing for me is it's easy to go in. I see certain of these podcast guys that go out there and they'll read directly out of the code book, and they'll be reading it wrong. And it just frustrates me, because it's like, dude, they're not talking about that, Like one of them, not trying to pick on this guy, but he says, "Oh yeah, you can't use EMT to support fixtures, but it's not EMT. It's two pieces of steel that are bolted up to the building." And then he's like, "Oh, well, you can't use a mini to hang a light fixture because it's not listed for that." I'm like, dude, I was like, it doesn't have to be. Nothing has to be listed to hold a light fixture up.
Nope. Sure
You know,
doesn't.
so it's just stuff like that it's like kind of trying to get better in the industry, and
Well, that's why you have these podcasts, because what I like to say to everybody is that, a lot of guys out there, they don't have access to go to school and stuff like that. They are in rural areas. And this is a good education opportunity where you're learning different aspects of the code and what the meaning is. It's sort of like when I do the proposed changes. When I'm doing those proposed changes and I'm telling you exactly what it says, I'm doing that based on the substantiation from the first and second revision of the code making panel.
Yeah, I really like that. You guys are definitely the first to do that for sure.
Yeah, in the next cycle, when I do the code changes, it won't be in the publication because it's got just too much text. But when I do the online course, there will be it'll transition. I'll do the NEC text and I'll do the first revision if it's there, and I'll do the second revision if it's there by the code making panel. Then I'll give an opinion and statement of what I think, based on those interpretations. And then from there, we'll have the illustration that will fully explain that illustration and what you're looking at. And I've never seen anybody, when you look at that, you actually could have a change that has 5 parts to it, explaining exactly what took place. And nobody has ever done that for the industry.
Well, and I like how you throw the code loops in there where it references all the different sections.
Oh, yeah. We've been doing that for a long time. And as far as I know, we're the only one that still do it. But we also have a table up at the top that tells you there's other standards that you can reference that go with that change, and you can go over and pick that additional information up. And we'll have the 70E document, 70B, OSHA subpart S, subpart K if it's for construction. And then we'll also tie in when we get to hazardous locations, for example, we'll tie in NFPA 496, 497, and 499. And then if you have industrial control equipment, then we'll tie in the other NFPA standards. So, we try to tie everything, NFPA 79, I meant to say that, but we tie all those standards in so you know what you're looking at, and you can have a correlation between the change and the other standards to have a better understanding of how it would apply.
Yeah, I agree. Yeah, excuse me. So the one thing that I really like about this whole experience is that we're able to just, come bring to you guys a bunch of different stuff. Excuse me. Like a whole bunch of different stuff from different angles, and really means a lot to me.
All right, let's kick off next. We got the topic of the week, so let me go ahead and cue that up, and then I'll cover this. The only thing missing from that intro is that ninja dancing. All right.
Go.
Now, what we're going to look at this week, we're going to be looking at electrical theory calculations. It's just basic calculations. And when you come over here, we've got a table. When you go over and you take in our publications or our online course, we basically go in and we show you a table of how to go in and do your amperes, where the horsepower is known, where the kilowatts are known, where the KVA is known. Then we show you how to do kilowatts, kilovolt amps, and how to do your horsepower. And these are all the different formulas you would use when you're going to perform these type of calculations.
Is that 746? Is that your horsepower?
Yes.
Okay.
That's the rating of 1 horsepower, 746.
Okay.
That's correct. And I'm going to show that here in a little bit. Now,
Okay.
when you come over and you look at these calculations, now I will tell you in the next cycle, all this is being updated. There's going to be a different color format. Everything's going to be updated. It's going to be a much cleaner, fresher look. And I can tell you, I've already posted some of the stuff on the groups, showing it to people, and everybody just loves the new color format. And I think it's going to be awesome. Now, for this one, what we're going to look at, if you look on the left-hand side and it talks about AC/DC formulas, we tell you what we're going to do here. We're going to calculate, find what the amperage is where just the horsepower is known, okay? So in order to help people understand how to perform these calculations a little bit easier, we'll come in and we'll put the known values that are in the illustration. And we'll tell you we have 5 horsepower. The voltage is 230 volts. It has an 80% efficiency, and the power factor is 90%. Okay.
Gotcha.
So when you go and look at step 1, you just put those values in that I just talked about. Okay. Now, one of the cool things about this is when you're doing this calculation here, before you ever get to this, we also have an example calculation with different values that we do step by step to show you how to calculate it. So when you get down here and you start calculating it on your own, you know how the formula is going to be applied in the steps that we do it in.
Okay? Right. And I'll be honest, the first time that I had something like I didn't really understand, and I went in your lesson and I actually understood it, and then I went and took it from like a test standpoint and I got it right, it was the best feeling in the world, because it was so hard for me to understand before you just walked it through step by step. And I didn't forget any steps. I didn't, I thought of everything that I was supposed to do in that calculation. And it meant a lot to me to go in there, understand all the different parts to it, not miss anything. Because there's different things that they want to ask you, like, oh man, did you remember 125%? Did you remember the D rate? All that stuff. Mm-hmm. And so I think that's awesome that you have all that stuff in there. Some of your stuff gets really complicated. So,
well, that's the really hard stuff that we get. I mean, that is for the advance. And, we have a lot of engineers that purchase our publications because they deal with some of them harder calculations. And we get calls all the time or emails just thanking us for having that information there, showing them how to put the values in and calculate, because they've never seen it before. And it's sort of like when you're doing where they'd come in and add welders, or they're doing something in healthcare facilities. I mean, we also get in where you have very large motor on the site, showing how to do that with a service calculation.
I will be honest, you're the only online publication I've ever seen that covered X-ray out of anybody. I've been out there a long time, and I've never seen anybody cover X-ray stuff.
Yeah, we do X-ray. We also go very in depth, showing you how to do calculations for fire pumps and how to size it based on the locked rotor current to make sure that overcurrent device doesn't trip, that the motor will burn up before anything. We also show you how to do it for a magnet circuit. We also show you calculations if you had a transformer and a high altitude installation. You don't see that in other publications.
Or the other one was actually do the voltage drop calculation, so you could show the inspector on your fire pump that you covered your voltage drop for that.
Yeah, you got to do that a little different, because you got running and starting. There's 2 different calculations you do for that. Right. And one's at 5 and the other's at 10%. And I, as far as I know, I've never even seen anybody do that calculation before, but we actually go through and show you that stuff. All right, let's get back to this problem. So This formula here, you're going to take the horsepower, multiply it by 746. So each horsepower is multiplied by 746, and you get that value. Then you're going to take the voltage, and looking at this is a single phase. So I don't have to put the 1.732 with this. So I'll just take 230 volts. Then I'll multiply that by the 80% efficiency, and then multiply by the 90% power factor. And then you take that value, divide it into your horsepower, and it's going to give you a value of 22.5 amps. Pretty simple.
Right. Yeah.
Okay? Now, the next one, we're going to show you how to do it where the kilowatts are known. Okay. So we're just going to show you an AC load here. And one of the things I'll point out, when you see the next cycle of the illustration, you're going to see that AC unit's going to be all colored up. You're going to see all the wire colors and everything that's in there, showing how it connects and all of that. And
nice.
it's going to look pretty sweet when we do it. Now, in this one, the kilowatts is 83.2 kW. You got 240 volts, and the power factor is 80%. You go over to step one, just put your values in. Then you're going to take that 83.2 and multiply it by 1,000. In other words, we're going to put it in VA form. And then we're going to take the 240 volts. It's a three-phase load, so I got to take that at 1.732, which will give me 416 volts. Then multiply that by 80% power factor, divide that in to your 83.2 times 1,000, and that's going to give you 250 amps.
Right.
Okay. Now, the next one you're going to look at is going to be where I'm going to do where the kilovolt amps are known. Okay. So we're showing you same type of setup. The equipment here is 104 kVA. It's 204. Once again, I'll take the kVA at 1,000 to put it in VA form. And then I will take the voltage, 240 volt times 1.732, 416, divide in that 104,000. That's going to give you 250 amps. So you can see we did the same calculation. Instead of kilowatts, we did kVA, and I still came up with 250 amps. And when we get over and we start looking at the applying Ohm's law and doing pi formulas and combining them, I'm going to use all the same values through there, and you're going to see we're going to get the same exact value when we apply that calculation.
Right.
All right. Now,
kind of like a cookie cutter.
Sure. Now, look at this. Now you've got 250 amps, 240 volts, 1.732 for the three-phase, and 80% power factor. Now, I'm going to take it back to put it in kilovolt amps. And if I go back here and look at the previous problem, what did I have? Let me go back here where I'm looking at it. 83.2. You see that?
Yep.
Okay, let's see if I get that same value here. I take the 250 amps times 240 times 1.732 for the three-phase, and the power factor is 80%. My KVA is what? 83.2.
Oh, nice. Came back out. There you go.
Yeah. And what we do in these calculations that I don't see other people doing is we take values that we're already using in other illustrations to show you the same principle applies. It just depends what values you have in order to get back to that known value you started with.
Right.
And that's exactly what we did here.
Nice.
All right. Now, looking at this one, let me go back because I'm going to show something here. Let me go back. This one here, you're going to see my KVA is what? 104. Okay, let's go forward. Now, here I've got 250 amps. Now, if I come back.
David Engelhardt had a question up in there. So couldn't you just use a 360 for three-phase 208 and 830?
Yeah. And actually, for the 480 volt three-phase, we use 831 because we round up to the next one. Instead of 830, we do 831. And then for the 240 three-phase, we do 416. and
Okay,
that's
gotcha.
based on the roundups way we do that.
Gotcha. Okay. Yep, you're right, David.
Okay, so if I come back and look at this, what was my amperage here? 250 amps. I'm 104 kVA there. Let's move forward. Here I've got 250 amps, like I've been doing, 240 volts from a voltage, 1.732 for the 3-phase. I multiply all those, divide it by 1,000, and what's my kVA? 104.
Yep.
So it's proven these facts that it doesn't really matter to me. It just depends on what known values you have. And based on them known values, you're seeing it's the same. It just depends what value you're trying to find and what information's available to you.
Right.
Okay.
And
Now,
David has a good point on that. That
sure.
once you nail that in, then you just use it every time.
Mm-hmm. And that's what I try to, when, I had to go do a class over at the Trinity River Authority, and they had an engineering firm come in a couple of years before, and they had some new guys. And I was going over it, and the guy that sat through mine, that sat through the other, he was the one that set the class up. I went through showing how all this works and everything, and he goes, we've had guys already take this with this engineering group. I don't remember the name of them. He goes, but we're going to have you come back out. We want you to show this to the other guys. He said, because this makes sense. We were having trouble understanding because they were all over the place with their values. He said, the way y'all set it up, he said, it makes sense because you can see how to take all these values and get the same information. Now,
Right.
If you'll remember, let me go back to the first one. I want to show you something here. Now, the first one we did was based on what? The horsepower, right?
Yep.
Okay. And what did we start with? 5 horsepower, right?
Yep.
Now I'm going to go back and I'm going to look at this calculation and let's see if I come up with 5 horsepower. So
you're reversing, you're inverting the formula?
Yeah, I'm inverting it. Exactly.
Okay.
I'm reversing what we're going to do.
Nice.
So I've got the same values here. The only difference I did different here is I'm showing you 22.5 amps for the motor instead of 5 horsepower.
Okay.
Okay. So I take here and I put the wrong amps there. I should say 225.5 amps. I missed it. I got it here. I just missed it. Then you take 240 volts, 80%, 90%. You take these and you take the 25 amps times 240 volts, time your 80%, time 90% power factor. Divide that by your 746 watts because you have 746 per watt. And that will give you a horsepower rating of 5.
Nice. So you freaking nailed it.
Just like we did in the previous illustration.
Awesome.
Isn't that amazing?
Yeah.
And
I always tell like students that that's the best way to do it on a test is to take like the answers and plug them into the formula. And as long as you know that formula, you can plug those answers in and just get them to make sense,
Sure. The only thing I tell people when it comes to the doing their motors and horsepower and getting the amperage or trying to figure out what the horsepower is based on amperage, all you have to do is make sure when you're doing the one to find the horsepower, you multiply the horsepower by 746 and then multiply and divide in all them other values, which is your voltage, your power factor, and your efficiency. And once you get that, you get the horsepower. Now, if you're reversing that formula, you do all the ones multiplying together, then divide by the 746.
Right.
And as long as you keep that in your mind, you ain't gonna have no problem understanding how to do your horsepower. And
nice.
a lot of people freak out on it because they see these formulas and stuff. But if you just remember the basics of the formula, you're not going to have a problem doing this basic electrical theory calculations that we apply, for our equipment and stuff. So.
Yeah, and that's what I really like about your program is it builds confidence. It doesn't teach you like how to pass a test or anything, but it builds you that confidence that no matter what that question is going to ask you, you're going to be ready for it. You're going to have those tools that you can pass it.
I've had journeymen that gone to take their masters. I've had apprentices that have gone to take their journeyman license. And I've received so many messages over the years that they've told Dad and I, they said, not only did I pass the test, they said, going through your courses, understanding how to do calculations and all the things you show, they say, I've actually become a lot better electrician just knowing that information and how to do it now.
Yeah.
And, one of the things that's interesting is I've had quite a few people that have purchased just the calculation course series. And the reason they like purchasing that is because I have it on a monthly subscription where I think it's like $30 or $40 a month. I don't remember. But the thing is, when they're on the job, they can take what you're looking at here where those steps are, and they can take and just plug in their own values there and do the calculation.
There you go.
And that's why a lot of people like these forms, because it's actually like a form, but I use it for teaching.
Yeah. Yeah. And that's what it's all about. It's all about giving all these people tools that they could use in everyday life. I mean, that's what my whole mission is to that was my whole purpose of creating Nat King Code, is to go in there, get the code and relate it to real life, relate it to what we do every day, I mean, a lot of times you get some of these code guys out there and they're just reading out of a book, and if they've never done it or they've never been out there in the field, it's really hard for them to interpret it the right way, the correct way, and go, okay, I see. Because when you're actually out there, me, for example, being out there in a Class 1 Division 2 area and seeing like, oh, hey, you could just use a regular 4-square box as long as it doesn't have make or break contacts.
Sure. And that's what makes all this so interesting is, we've spent, God, I guess between Dad and us, these books have been developed, I guess, 40 years at least. And all the stuff that you see in here has come from years and years of teaching. And as we've been out teaching, we started noticing, it'd be better if we did this. And then we get a lot of feedback from the people that are attending class saying, hey, can you do this? Can you do this with it? And we'll make those notes in our publication. In the next cycle, guess what? We update it.
Yeah, that's awesome.
All right. Now let's look at basic Ohm's law. When we teach this, I'm actually going to take in the next cycle, and on the left-hand side where it's in the black, I have a little illustration that shows where you put the thumb over it. So in other words, if I put the thumb over the E, then I'm going to multiply I time R. If I put the thumb over the current, then I'm going to divide the resistance into the voltage. And if I put my thumb over the R, I'm going to divide the current into the voltage. Okay.
So your thumb would mean what you're trying to find?
Yes.
Okay.
And what I did in this and in the last one, I just colored up top to show you we're going to be doing the voltage here. So, and you look over at the exercise problem and you look in step 2, we tell you it's E equals what? I time R. So you're going to multiply those together because they're across from each other. Right. Now, the known values here, we're telling you we got 0.645 amps and we have 160 ohms of resistance, or 0.186 ohms resistance. So I'm just going to take those two values, multiply them together, and that's going to give you 120 volts. Okay.
Right. Pretty
basic. All right.
Yeah.
Now, when I do the current, same values, we had 120 on the voltage. So I'm just going to take the 0.186, divide it into 120, and you'll get 0.645 amps like what was in the original illustration. Okay.
Right.
And then if I'm finding the resistance, I'll take those two values, which was 120 volts and 0.645 amps, divide that into 120, and it gives you 0.186 ohms. Okay. Right. You'll see I use the exact same values, didn't change anything except for what? The formula.
Yep. And that makes it easier to learn too.
Yeah, it does. Now, what'll happen, then you get in and you start looking at pi. Same concept here. Mm-hmm. If I'm wanting to find the power, I time E. If I'm wanting to find the current, E divided into P. And if I'm wanting to find the voltage, I's divided into P. Okay.
Right.
And then I'm going to show you, after we get through this, I'm going to show you combining those Ohm's law and pi formulas where we add the resistance into it. Okay.
Okay. Okay.
So here I've got 31.25 amps and 240 volts, and I'm finding the power. So I'm going to multiply it. That's going to give me 7,500 watts. Okay.
Right.
Then if you look here, I'm going to find the current. So I'm going to do the same thing. We had 7,500 watts like we just calculated. Divide 240 into that. It'll give you 31.25 amps like we just calculated.
Right.
Then if I'm going to find the voltage, I'm going to do the same thing. Take the 31.25 amps, divide it into 7,500, and that gives you 240 volts. Pretty basic. Okay. Now, you're going to see a whole different setup in this next one. You're going to see we have a different wheel up there that shows you when you're finding the power, you're finding the current, you're finding the voltage, or you're finding the resistance. Okay.
Right.
Now, if I look at this and I'm just doing the first one here, and my known values, I know and I'm going to find the power here, and I know what the voltage and amperage is. I'm going to do it just like I did before. You take E time I. All right. So I'll take the 120 volts times 0.645, and that's going to give me 77.4 watts. Okay. Now, when I come over here and look at the next one and I add resistance into it, all I'm going to do here is I'm going to divide the resistance into the voltage. So I'm going to take the 120 volts, divide 0.186 into that, and that's going to give me 77.4 watts. Okay. Now, the only thing I will point out here is when I'm doing this, that voltage has to be squared. Okay. And we're showing 120 volts. I should put square on there in that third step, or I'll change that and just put what it is squared. But when you square that and divide the 0.186 in there, that's going to give you 77.4 amps. Matter of fact, give me 1 second. Let me open my book here because I want to change that. I don't like the way that looks. Okay. All right. Yeah. I know what it's supposed to say, but that needs a little bit more clarification because that is squared. Okay. Now, the next one, when I come in and I know what the amperage and resistance is here, you're going to square the amperage and then multiply the resistance. So I want to point something out here. If I'm looking at Ohm's law, okay, I always take and divide the resistance into the voltage. Is that correct?
Yes, sir.
Okay. The only difference that's applying here when I'm finding power, it doesn't matter. You're going to square the amperage or you're going to square the voltage when I'm finding the power. That's how you want to remember this formula. It's like a little teaching technique. So
okay.
if I come back and I look, like I won't go back, but if you look up here and you look in that green portion of the wheel, you'll see where the voltage is. I squared it. Okay. And I divided by R. Okay. Now, if I was just finding amperage, I'd just take R divided into what? E. But if I'm finding power, I squared here. Now, if I'm finding the voltage here and I'm looking for voltage, I would just take I times R. But since I'm finding power, you're going to square the amperage here. You'll have
now the power. Now the power, does that represent watts or volt amps?
No, it's squared where it's your amps. You're squaring the amps.
Okay. I'm just saying, like, if you're finding power, is that you're finding watts?
Yeah, you're finding watts. Yeah.
Okay.
Yeah,
Gotcha.
the power, you're finding watts. Yeah. So, and I need to do this here. I've got it at 0.645, but I'm going to put this where I'm going to put a square on there because I know it's supposed to be squared because you're looking at the formula, but I'm going to change that because I think that would be better clarification. But
looks like David knows what time it is.
I have a pi wheel clock at work. Yeah, brother. So you would take that 0.645 square it and then multiply it by 0.186, and that'll give you 77.4 watts. Okay. Now, the next one I'm going to look at is finding the current. Okay. Now, if you notice here, what they're going to do is when you do the current, we've already looked at the Ohm's law and pi formulas combined. So if I'm finding current, E is divided into P. And then if I'm applying the Ohm's law, then of course the resistance is divided into E. And then what you're going to do, if you're finding it with the power and resistance, you're going to take the resistance, you're going to divide it into the power, but you're going to take that whole formula and you're going to do what? Square it.
Yep.
Okay. That's all you're doing. But you notice it's the same concept. I'm just taking here and I'm taking, instead of squaring one value, I'm just applying the original formula, R divided into P, but I'm going to square it here.
Right.
Okay? So the first one I'm going to look at is finding the amperage. It's a basic 120 volts times 0.186 like we did earlier. That gives you what? 0.645. All right.
Yep.
Then I'm going to come over and I'm going to look at doing it with the known values where the power and resistance are given. And I'm going to take that 77.4 watts and I'm going to take that, I'm going to divide it in by 0.186, and then I'm going to square it, and it's going to give you an amperage value of 0.645. Now, the thing I want to point out, have you noticed any of the values changing?
David Englehart asked, what is the difference between watts and volt amps?
One's put in VA form and one's not. That's basically it.
Yeah, the watts is power potential and the VA is power used, I believe.
That's correct. And that's what I'm saying. One will be put in VA and one's not.
Right.
Because the VA is where you're going in and you're applying it as part of the calculation. Matter of fact, if you look at our calculations that we do in our publications, when we're doing full calculations, it doesn't matter if we show something in watts, we always put it in VA when we're doing the final calculation with everything.
Right.
Okay.
That's how you get more accurate with your calculations.
Now, if you look at this, this is where we're going to look at voltage. Ooh, I've actually got one extra green on there. I need to fix that. Apologize for that. I must accidentally click that. All right. So when I'm looking at the voltage and I know the current resistance, what do? I multiply them.
Yep. So
I'll take the 0.645, 0.186 for the resistance, and that's going to give me 120 volts, just like we did before.
Mm-hmm.
Okay. Then I'm going to come over and I'm going to say, see, that's the way the wheel should look. I accidentally clicked one over. Now, if you look at this, based on the pi formula, and I'm finding the voltage, I'm going to divide the amperage into what? The power.
Yep.
So my wattage here is 77.4. I take the 0.645, divide it into it. It gives me what? 120 volts.
Yeah.
Okay. We're in the same values. Now, watch this. Now I'm going to do the resistance. Now, excuse me. There's one thing I want to point out here. Anytime, and anybody that's watching this, I want you to pay attention to what I'm saying here. If I'm taking and I'm finding the amperage or the voltage, and I include the power and resistance in the calculation, there's only one difference in both of these. You're still going to square the whole thing. The only difference is if I'm doing for the amperage, I divide the resistance into the power, but if I'm doing the voltage, I take and multiply the resistance and power. Okay. And then I square it. Okay. That's it. Okay. That's the easiest way to remember that when the resistance is involved in the calculation. Gotcha. So okay. I'm going to take the 77.4 wattage, and then I'm going to take the 0.186 for the resistance. And then I'm going to take and I'm going to square that, and that's going to give me 120 volts. Now, so far, as you can see, not one value has changed here. So the last one is finding here the getting into the resistance. And when I take my resistance and I have the voltage and the amperage known, I divide the amperage into the voltage, just like we did in Ohm's law. So I'll take
Right.
the 120 volts, divide it by 0.645, and look at that value. It's still 0.186.
Right.
Okay. Now, the next one I'm going to look at, I've got the power and current. Okay. Now, the only difference here is you'll notice I'm going to take that current and I'm going to take the current and I'm going to square that current and then I'm going to divide it into that power. Okay. So I'm going to take 77.4 watts, take the 0.645, square that, divide it into the 77.4, and that's going to give you a resistance of 0.186. Okay. And then the last one that will be for today is taking and doing the resistance where I have the voltage and power known. And all I'm going to do here is I'm going to take that voltage, I'm going to square that. Oh, I got those upside down, don't I? I sure do. So I apologize. I was doing this late at night trying to hurry up at the end. I was up till 3 o'clock in the morning doing this.
Well, we really appreciate all your work. And like, this is so awesome. A lot of my apprentices say that they learn so much from these, and it means a lot to me.
Well,
You spend so much time working on these.
Well, if you take that power in the step 3, I guess I was just looking at step 1, just drop the values down, but in step 3, the voltage should be 120 volts squared, and then you divide the 77.4 watts into that, and that'll give you a value of 0.186 for your resistance. Right. Now, the thing that I will point out here is all of this that I went through, there was a systematic way to go through it. And if you notice how we went through all of that, it all stayed exactly the same calculation wise. I used all the same values. The only difference is there was a little bit difference in the formulas when you were applying that wheel right here. And when you're looking at this wheel, just remember a couple of the steps here to help you remember how to do that calculation. And what I've learned over the years, we start with this in our journeyman book, and we even do it in our master's book. It's a refresher in case they're asking you questions how to perform these calculations, and you remember how to use those wheels, whether you're doing just Ohm's law, pi formulas, or doing a combination of the Ohm's law and pi formulas combined.
Right. I'm gonna have to put one out. I have one that is a pretty tricky one that I can post that you need to use that. So
yeah,
and it gets a lot of people where they just try to do the simple way, and then it's like, no, you have to factor in the resistance is a constant on certain heating loads.
Sure. And that is a great setup for how to do electrical theory. And I always say this, a lot of people forget that basic electrical theory and how you apply it as it relates to our electrical equipment. And those formulas there, those are the most important formulas you're going to use in the electrical industry. And as long as you have that concept down, you're not going to have that much problem understanding. And it helps you when you get in and you start looking at the code rules and stuff and the direct correlation as it applies to the electrical theory. Because we actually do some problems where we make you do the electrical theory in order to do the calculation. So that's bring that back to you.
You know what I call it? I call it easy math. I always tell my apprentices, just do easy math, man. Just don't do the hard math. Do the easy math, because that's my number one problem with the apprentices these days. They overthink everything.
Sure, they
and
do.
If you overthink it, it's gonna make it way harder. So the more easy I can make it to explain it, or you can make it to explain it, and you're like, dude, I'll tell you what, I am really stoked. I can't wait till you get state of Colorado, because I'm already sending you my application for the minute that you get that state of Colorado, because I'm ready.
They're coming, and it's I guess it's COVID and everybody working at home. And I mean, they've actually told me I've had about 10, 12 states tell me they never received the stuff. I'm like, you got to be kidding me. I sent everything in. And it's just they're not going to the office, or they go and something gets in another file or something, like one of them, I was trying to remember the state, they put it in somebody else's over there and they picked it up and they threw it in the trash, come to find out. I mean, it's just ridiculous, but I'll eventually get them. I'm not worried about it.
Yeah, all that's cool.
You ready to do the new code changes?
Let's do it. I'm down. All right, I have my first complaint on music. We can't use the same music twice, man. Like, we have to have new music, man.
All right, I'll put a new one in there.
No, I'm sending you one. I got a new one. We're gonna have our code change music.
That song just cracks me up.
Oh, even David Englehart over here.
Thank for on-demand availability. No worries, brother. Have a good night, David. All right, now. This is getting into the new code changes. We'll be looking at 225.42A through E through 230.67A. Now, this particular one, I actually saw yesterday when Mike was sort of touching base on this, and it sort of seemed like he was throwing the manufacturers under the bus to me.
Hey.
But what this is talking about your surge protecting devices, and it's going to discuss where they shall be installed. And you're going to see all the new areas, and they're going to tell you areas such as dwelling units, dormitory units, guest rooms and guest suites of hotels, motels, and also areas of nursing homes and limited care facilities used exclusively as patient sleeping rooms. Okay.
Well, I'll be honest with you. I actually like this change. I didn't like it at first because I kind of thought, how is it the code's job to shove this down people's throats? But, and Corey Hanna made a really good point. He's like, dude, we have like $10,000 worth of computers in our house,
Sure.
and so, and that you're spending maybe an extra like $20-$30 for have SPD main on your panel. Who cares? And then to kind of rebuttal what Mike was going on, he was saying that you'd have to have SPD protection for each unit. That could be accomplished with a Type 2 SPD at your.
Sure could.
And so that would be compliant for however many units you wanted. You wouldn't have to have it for each individual breaker for that multifamily dwelling unit.
That's right. And that's why you got different surge protection devices types. It's just for that reason. And then they just tell you the location it'll be installed or adjacent to the distribution equipment. And then they come in and tell you your different types like we were just discussing. And like you were saying, type 2 for those multifamily. And then it talks about replacement. And it says where you have distribution equipment and you have it supplied by a feeder, then it tells you all the requirements in this section here shall apply. And then it talks about the rating of it, and it tells you it won't be less than 10 KA.
Right.
That's it. So I think that's for me, it's okay change for me because I actually already have it at my place. So, I'm not worried about it.
I think it's fine. I think it's an okay change.
I do too. Now, 230.7 is going to talk about your other conductors, then, of course, your service conductors. And they've added some stuff here to clarify this. And they tell you they shall not be installed in the same raceway cable. And then they added handhold enclosure or underground box as the service conductors. I never had a problem with this. I always said you couldn't install the other conductors with the service conductors, but apparently they were doing it in these mainly underground boxes from the documentation I read, and they wanted to clarify that those couldn't be in the those conductors, other conductors couldn't be in these enclosures as a service conductor. So it's more of a clarification to make sure nobody's doing that.
Gotcha. Okay.
All right. And of course they go in and tell you that to limit the exposure. Now, this and I thought was pretty interesting, and usually I don't do a change where they just add a section, but in this case, this is important because they tell you here, service conductors shall be permitted to be spliced or tapped in accordance. And I thought it was important because 230.46 specifically deals with what? Taps or splices. And this is getting into there, letting you know that if you look at 230.46 and you're in compliance with that, that's where you get into those taps and everything for those service conductors.
Gotcha.
So
okay.
They're just, it's more of a clarification for the installation of the splice conductors.
Gotcha.
Okay? And that's what they're telling you here for further detail on the splicing for those type of service conductors. It's just a clarification that's added to let you know, look at, if you go back and look in our publications, we automatically refer you to this section anyway. So this was actually an easy illustration for us to do because we already had it.
Nice.
All right. Now, this one is important because this is going to talk about your service equipment where it's enclosed or guarded, and it's going to talk about the barriers that are placed in service equipment so that no uninsulated or ungrounded service bus bars or service terminal is exposed to what? Inadvertent contact. And that's where people are doing maintenance on the equipment while they're servicing what? The load terminations. But it tells you here, you're servicing those load terminations with the service disconnect in which position?
Open
position.
Yeah, we ran into this a lot out at the freaking peanut butter and jelly factory and peanut butter and jelly sandwich factory. But they have a lot of equipment that comes from overseas and they don't comply with this.
Sure, they don't. And that's why it's in here, is to make sure, they think just because you have the barrier in there, that takes care of everything. No. And why is that important? One of the things, the barrier is there to protect you from what? Electrical shock. But if you got in there, something dropped or something, you think that little barrier is going to protect you from an arc blast? No, it's going to knock it right off there. And that's why they're telling you that the service equipment, when you're servicing those load terminations, it's in which position? The open position. That's why it's there. So it's more of a safety thing. That's really, in my mind, it's in compliance with 70Es the way I look at this. And what they tell you here, they're telling you the revision clarifies that the intent of this section is to provide protection for exposed service conductors and circuit parts that are where? On the line side of the service disconnect or overcurrent protection device or disconnect. And that's what I'm saying. Those are still energized. So that barrier is not going to protect you from an arc blast. Okay.
Yeah, and they do have some pretty good barriers in there, but you have to just be careful when you're in those overseas equipment.
Sure. Now, this is interesting because they're talking about surge protection devices again. And they tell you the following occupancies, and you're going to see the exact same occupancies here. Okay. This is, I was going to, if I hadn't knew this was in the slide, I would have covered it ahead of time for next week. But since it fell here, I was like, I'm good. So what we're getting into here is these surge protection devices. And when you look at these surge protection devices and you have these set up here, this ties in with 230.67. Now, look at this. They're going to tell you here that electronic life-saving equipment such as fire alarms, they just go through your AFCIs, your GFCIs, all that. and it say may be damaged when a surge occurs due to lightning, internal local switching, as well as an external utility switching. What they're basically coming in and telling you is you're putting this surge protection on to provide, because let's say you got a lightning and you blew up your fire alarm or something like that, then all of a sudden you've got a problem because if something happens, that unit's not working anymore, is it?
Dude, I'm gonna say that's probably a Willie Jackerson code.
Yeah, well,
he probably unintentionally hooked up some 4160 to an apartment building or something, and they said, you know what, we're gonna have to avoid this.
now before I get off of that, I want to explain one more thing. You know, because I've seen this happen, and the only reason I know this, my ex father-in-law, he has a really nice place at Possum Kingdom Lake, and everything out there that he has operates on Crestron. It's like a smart house, basically. It controls everything at the house. Well, what they did, they had a unit. I mean, they literally had a full setup unit and everything where everything was controlled. And then it was over in like this little tower area they had. And then they come down and they took and set a bar there and they connected everything there that come down. And then they went outside to the grounding electrode. Now, yeah.
Weakest link.
That's right. So that Crestron unit become the shortest path to ground for any incidental energy or anything, and it was blowing boards. They couldn't figure it out. They had all these engineers out there, and he calls me up and he says, James, he goes, I know you know all this stuff. He said, would you please come out here and look at it for me? I'm already divorced from his daughter, but him and I still have a great relationship. And I said, yeah, I'll come out there. And so I went out there and I started looking. I said, okay. I took that bar off right there. And then I took and went and got another bar, and I brought everything else coming down. And then I took and tied everything coming up, you know, and we took another grounding electrode off of that unit down there separate. And then I isolated everything back to where 1 point.
Yeah.
And the engineers were out there and they were going, what are you doing? You're messing our unit up. And I said, no, I'm not. I said, you guys don't know what you're talking about. And David, he was funny. He goes, all I know, it's not working, and I'm going to do whatever he says. He goes, he teaches this stuff. He's been all over the world. He goes, I'm listening to what he says. And we did that, and they put those oscilloscopes on there and everything. And guess what? They've never blown another board.
Dude, you would love this story. So I got called by a dealership, and they had like an automated phone system.
Mm-hmm.
And they call me. This is really funny. And they call me and they said, yeah, we got too much resistance to ground.
Mm-hmm.
And I said, oh, okay. So we just got done doing that dealership. So I'm like, okay, whatever. It's brand new. Everything's fine. So then I'm like, all right. I was like, yeah, I'll go look at it. So I get over there and the module is plugged into an isolated ground receptacle, you know? So I'm like, oh, okay. And so I unplug it and he's like, oh, wow, it went away. I was like, well, yeah, I just unplugged it, you know? And he's like, oh no, it has to be something with your stuff then. And I was like, oh, all right. So I'm getting ready to go plug it into like the normal power. Oh man, those dudes were like diving like I was getting ready to like pull the pin out of a grenade, you know?
Oh yeah.
And it was so funny because I said, you know what? If I was you, I'd check that module to make sure that you got, you know, check your resistance. Turned out it was a bad module and it was backfeeding on our system. Sure. You know, and the whole thing was it had nothing to do with the clean ground. Like to me, I was like, dude, you guys, I mean, it was the same exact thing. It was just those receptacles didn't touch the equipment grounding conductor. They just basically went on their own isolated path to a separate ground rod. They went to a separate isolated system in the service, but it was it was all pretty much the same exact thing. It was just those ones didn't touch the equipment ground. And it was funny because I was checking resistance, and I'm like, okay, I check resistance on the IG. I got like 42 ohms resistance or something. I go check resistance on the dirty ground, and I got like 0 because it's connected to everything.
Yeah.
I was like, oh, we just got to put it over here. He's like, no. It's good. We got it. We got it figured out. And I just thought that was a funny way to say, I don't think you guys know what you're talking about.
I remember it's probably about 10, 15 years ago somewhere there, I was doing a grounding course, and a guy told me, he goes, well, how would you set up your clean grounding system? And I said, what's a clean grounding system? I've never heard of that. And he goes, that's where it just goes to your electronic stuff. And I said, well, first of all, there's no such thing as clean grounding system. I said, what you're referring to, I said, you always want to get everything back to one point. And
right.
I showed him how to do it and everything. And he goes, oh, and what they had this basement, and they had this ground bar all the way around the room, and they were coming down, hitting this ground bar all the way up from all these units from all different levels. And of course, they're picking up shorter paths. I mean, there was currents going everywhere, and they couldn't understand why they were blowing all the lower floor boards and stuff, because that ground went outside in the to the equipment. And when you got out there, it was about 20, 30 foot away, and everything else is inside here where you had all these shorter distances. They're blowing. They just couldn't understand that. And I said, that's not a clean grounding system. I said, you're creating more potentials all through here where you're picking up all kinds of stray currents and shorter paths. And I said, you need to get rid of this whole thing. I mean, it looked really nice, but it wasn't correct. And then after I showed them how to do it, and we brought everything into one bar that was closer over here and took it out to the service equipment, to one point, they didn't have any problem after that.
Well, and we ran into that stuff before out in gas and oil, where we ran what we call a triad ground, triad system. And that's for like your control systems and keep the noise off the VFDs and stuff.
Sure.
And then people just like, hey, green equals ground, and they tie them together. And then that's when you get problems. And dude, I was blown away. These dudes, when they had these millwrights come out, and Lemonhead will tell you about this too. They were sitting there checking the voltage across the bearings of these motors.
Oh, really?
And they actually had to ground the actual motors to where they had 0 voltage across those bearings. Because what happens is those bearings, they'll spin and they'll actually create like an inertia. They'll create like their own kind of voltage, and you have to dissipate that within a certain tolerance. But Lemonhead tell you more about it than me. He was in there showing me what they were doing, and I was like, wow. I was like, that's pretty cool. I mean, you had to sit there and like clock them. They have to like clock them to where they get them to the right where they hit the right polarity, so where the polarity's at the right thing. And it was some interesting stuff. Like, I learned a lot, like checking that stuff out. I was like, wow. I was like,
you're going to learn a lot when you're doing that. In fact, in our publication, we show you how to do those triad setups and everything. And I was trying to think. I think our grounding chapter has, God, I bet it has around 150, 60 illustrations in it, just going through Article 250. And then we tied in also with NFPA 780, where you're dealing with just the basic lightning protection for buildings and structures. So we go through all that stuff.
Well, and I do have a confession for everyone. My tool review this week is not necessarily a review. It's a new tool that I heard about through Knipex Tradesman, the Knipex Tradesman group. And, one of my friends runs the Knipex Tradesman group, and I always try to at least pop in a little bit of Knipex stuff, even though I don't own any. but I've heard a lot of stuff about how awesome this new tool is. So we can run the tool of the week.
Let's cue it up.
It's time for Tool Review of the Week. Sponsored by Electricians Only Tool Review and Knipex Tradesman.
All right, so I've heard a lot of great stuff about these. They're not necessarily strippers. They're basically what you call multi-tool. So you're able to use like the tips of them as like a lineman. You can strip with them. And then I guess the number one feature that the Knipex people are bragging about, and we actually have in our Knipex tradesman group, we actually have the sales representative in there. So she's like the vice president of sales for Knipex. So if you have any questions, you could always tag her on stuff and they'll tell you. But what they're really bragging about on these ones is you could take a 632, a 832, a 1032 screw, and you could just straight cut them with the cutting blade, and they'll thread right in. So that's supposed to be the big rave on these. I haven't officially tried them yet. I really want to, and I'm kind of curious about how much they are. I would bet that they're probably like $30-$40, but I might be way off. I'm not sure. Usually the German made stuff is pretty expensive, but Knipex is actually starting to manufacture products in the US. So they're still the high quality. They still use the high quality steel. They still do all the same stuff that they do over from Germany, but they're just doing it here in the US. So I'm real excited about that. And I'm real excited to actually buy me a pair of these. So we might have a follow-up review on this one. And I might say, you know what? They suck as linemen or whatever. I don't know. I would not use like anything smaller than whatever my linemen's are to try to twist wires together. But, you know, I'm a fire alarm ninja. So I might, use that for fire alarm. Might be a really good fire alarm tool, so.
Cool. All right.
Yeah. I will actually do a follow-up, and we will revisit some of the tool stuff. And if you guys have a tool that you really like or you really hate, I'm fine with putting it in there. Like if there's something that you guys are like, dude, this tool sucks, then we'll run it. We'll put your review in there and I'll run it and I'll say, you know what? Do not buy this piece of crap.
Just tell you, it sucks.
Well, one of the ones that I should do a review on, I mean, of course, I'm not going to go off on hook drill or anything, but there's the one where it's like a fish thing where you can like drop a metal thing in the wall, and then you could take a magnet and you could fish things through the wall with the magnet and stuff. And I just hear so many people complain about that because there's so many magnetic things in the wall that they drop it in there and then they get it all stuck in there and they can't get it out, because there's so much. There's like screws and there's metal studs and I guess it's supposed to work for like residential, but reach out to me, guys, if you want me to start covering just like negative reviews on stuff. We'll do that too. I'll go through and just like you reach out to me, show me some bad products. We could do a review on the hook drill. I think we have a few members that talked about the hook drill. It's basically a hose clamp that clamps a thing on, and then you like, I don't know. It's supposed to be a drill press for your cordless, but I don't know. It didn't seem to float too good. And then it actually, I guess, he even made hook saw with a shelf bracket or something. You put a shelf bracket on your skill saw or something, but I don't know. We'll start looking into that in the future. I'm trying to bring tools to you guys that I use and I like a lot, and try to get that out there, different stuff that will help you guys out in the field.
Sure.
But we could do something funny, do all the negative reviews.
Yeah, we can do anything we want. That's why I like the podcast. We just do whatever the heck we want. Now, I will tell everybody next week you'll see we're actually going to have Dad on, and he's going to explain the difference between intrinsically safe circuits compared to non-incentive circuits.
Dude, I'm really excited. I'm going to learn a bunch too, man. That's going to be awesome.
He's going to go through it. He just did a class over at BPI, Building Professional Institute, and was explaining all that. And there was a lot of people in there said that was the best hazardous class they'd ever sat in. So
nice.
But you know,
I'm excited.
That comes from years and years experience from dealing with the chemical industry and the oil and gas industry. You know, we've done so many classes there. You know, we wrote the inspection report for them on their pump stations and everything through Alaska and all that. Then we come down, did it in the Houston area for them. So we've got to see a lot of stuff people don't get to see because usually those locations are off limits to everybody else. So, you know, based on that, you know, and when we were up in Alaska, we were actually working with ACOSH on all of that too. And after we finished putting the report and everything together and how they were going to use it, ACOSH said, y'all do this, we'll prove it. So,
well, you know, the picture that I had, my famous picture with me and Lemonhead, actually that was on a plant where if you're an inspector, you have to get invited in there. Like, you can't just walk in there and just go, oh, fail 11026. They'd be like, what, dude? Like, nah, dude. Like, go back to your city of like Fort Collins or whatever. You know, like, not trying to pick on Fort Collins, but you know, go back to your city of Longmont or go, you know, whatever. I'm not trying to pick on any inspector, but if you're like a city inspector and you go out to one of those gas and oil plants and you start citing all these weird code violations, they're going to look at you like you're dumb, you know, like, dude,
sure they are.
Like, dude, this is a 4160 gear. You're not going to take this cover off. Like, that's why I thought it was a really cool opportunity to take that picture, because that, I guarantee those covers have probably never been taken off ever since that's been energized. And they probably won't for a very long time, you know? And so that time of us having all that gear open, some of those sections in there, I didn't remember when it all happened. Some of those sections were 13.8.
Oh, okay.
So
yeah, 13.8 kV.
Yeah, some were 13.8, some were 4160, but they even had stovepipes in there where the 13.8 was on one side and the 4160s on the other. But
yeah, we've been in a lot of locations where we've seen that, and we've also been in locations where they basically control their own power supply right there, and you know, and they're actually applying National Electrical Safety Code rules. And then also with inside there, they've got NEC rules. So we've been out there to help them make sure they're complying with that too. And we combine that with not only OSHA subpart R&V, but also the National Electrical Safety Code.
Dude, we're at like 1:30. It seems like it's probably about Pop's dinner time out right now.
Yeah, I'm actually at the office. We're going deep tonight. And
nice.
We're going, matter of fact, I have to make it pretty quick because they close at 9. We're going down to have Italian beef sandwiches.
All right.
Yeah.
Sounds great, sir. All right. Well, badass show. Appreciate you.
Same here. And everybody have a good week. We'll see y'all next week. And don't forget, you know, anybody that wants to join any dummies, pass it around because it's a growing fast.
It's awesome.
All right. Everybody have a good week, and we'll see y'all next Thursday.
Peace. Special thanks to all the members of the NEC Dummies for joining our content. Special thanks to the High Voltage Live. Special thanks to David Engelhardt. Thank you for joining tonight, sir. Very awesome to have a guy like David Engelhardt in the audience. super awesome. Thanks to the NEC Deathmatch, the best competition known to electricians. Thanks to the lady electricians. Awesome to have the lady electricians in the audience. Thanks to the NFPA 70E discussion group. Always engaging. Thanks to Mark Candel's estimating. Appreciate you, sir. Thanks to Hobbles Live Electrical Meetings. Awesome.